General relativity. General relativity was published in 1915, 10 years after special relativity. Special relativity dealt only with inertial frames, but that is quite literally a special case. In the real world, gravity and acceleration exist, and they needed to be incorporated into the theory. General relativity is the extension of special relativity that handles any reference frame, not just inertial ones. Einstein concluded that gravity is not a force, but a geometric phenomenon, a curvature of spacetime caused by mass and energy. He then formulated the gravitational field equations, expressing the relationship between that curvature and its source, the energy-momentum tensor. In this series, we have already derived the right-hand side, the energy-momentum tensor. Here, we will derive the left-hand side. But first, let us trace the reasoning that led Einstein to the idea that gravity is the curvature of spacetime. Note: compared to special relativity, the equations in general relativity are more complex and the derivations longer. However, as always in this series, we will not skip any non-trivial steps. When we work through lengthy calculations, we will say, "Please pause here." At those moments, feel free to stop the video and follow the equations at your own pace. Two kinds of mass. The mystery. Newtonian mechanics could not explain. There are two ways to measure the mass of an object. The first uses gravitational force. Here, mg is the gravitational mass, a measure of how strongly an object responds to gravity. The second uses acceleration. Here mi is the inertial mass, a measure of how resistant an object is to acceleration. These two masses have different physical meanings. However, since both equations describe the same force F acting on the same object, they can be set equal to each other. Here, m is the mass of the Earth, and r is the distance between the object and the center of the Earth, which can be treated as a constant near the surface of the Earth. Near the surface of the Earth, the acceleration a equals the gravitational acceleration g, so F equals inertial mass. Times a can be written as F equals inertial mass times g. Setting the two expressions equal gives since g is always constant at 9.8 meters per second squared, regardless of the object, the ratio m sub g over m sub I must equal 1 for all objects. Therefore, m sub g equals m sub I. Newtonian mechanics had no explanation for why this should be the case. Today, experiments have confirmed this equality to a precision of better than 10 to the power of -15. Einstein took this a step further. He proposed that these two masses are not merely numerically equal, they are the same thing. What can we conclude from the equality of gravitational and inertial mass? Since m sub g equals m sub I, this simplifies to this means that gravitational acceleration is a constant, independent of the mass or nature of the object. Every object falls at the same rate. Consider the electromagnetic force. It depends on the electric charge of an object. A highly charged object feels a strong force, while an uncharged object feels nothing at all. The electromagnetic force is a property of the object itself. Gravity is different. Heavy or light, all objects fall at the same rate. Gravity does not care what the object is made of. Simply being at a location is enough to experience the same effect. Could it be, then, that gravity is not an interaction between objects, but rather a manifestation of the nature of spacetime itself? Equivalence principle. We have established that all objects fall with the same gravitational acceleration. This leads to a remarkable conclusion. As a thought experiment, consider an elevator in freefall with a person and an apple inside. Freefall means the object starts from rest and falls straight down under gravity alone. The moment the elevator enters freefall, the person and the apple become weightless. Since every object falls with the same gravitational acceleration, their relative positions no longer change. Both the person and the apple float freely inside the elevator. From the outside, an observer sees the elevator, the person, and the apple all falling together under gravity. But from inside the sealed elevator, with no windows, the person has no way to tell whether they are falling toward Earth or simply floating in gravity-free space. In other words, by moving to a freely falling frame of reference, we can locally eliminate the effects of a gravitational field. We have seen that the effects of a gravitational field can be locally eliminated. Now, let us see that the reverse is also true. Gravity can be created. Imagine a rocket accelerating upward at 9.8 meters per second, squared in gravity-free space. The person inside feels a normal force from the floor pushing up against them. This sensation is completely indistinguishable from standing on the surface of the Earth. This means that a system at rest in a gravitational field and a system accelerating in gravity-free space are physically indistinguishable. This equivalence between gravity and acceleration is known as the equivalence principle. Einstein himself referred to this realization as the happiest thought of my life. Let's explore what can be derived from the equivalence principle by looking at actual physical phenomena. Imagine you are inside a rocket that is continuously accelerating upward. Your viewpoint is in a co-moving frame placed at the origin O of a coordinate system that moves together with the rocket. Let's consider the trajectory of light as it enters from the left wall of the rocket and travels to the right wall. Since the rocket is continuously accelerating, the light actually curves downward to the right, tracing an arc, as seen by the observer inside the rocket. On the other hand, for an observer in an inertial frame outside the rocket, the light simply travels in a straight line, passing through the rocket. Why did the light curve? When the rocket is in uniform inertial motion, light travels in a straight line for both the observer inside the rocket and the observer outside. The light curved because the rocket was continuously accelerating, and since the equivalence principle tells us that acceleration equals gravity, this phenomenon can be restated as light is bent by gravity. However, from the standpoint of Newtonian mechanics, this is a contradiction. According to the law of universal gravitation, a mass m sub g is required to receive gravitational force. Furthermore, according to the equation of motion, light, which has zero mass, cannot be deflected by any force. In other words, within the framework of Newtonian mechanics, light can neither be affected by gravity nor bent by any force. However, the fact that light curved inside the rocket is not an illusion or a mere appearance. It is an undeniable physical fact in the accelerating frame. There is a fundamental principle in physics. Light always travels in a straight line along the shortest path. To explain this curvature without contradiction, the most natural interpretation is that space-time itself is curved, and light simply traveled straight along the shortest path in that curved spacetime.
So what curved spacetime? According to the equivalence principle, the interior of an accelerating rocket is equivalent to a gravitational field. And wherever there is mass, a gravitational field is generated. Einstein therefore reasoned as follows: mass curves spacetime, and within that curved spacetime, light must bend in the same way as it does inside an accelerating rocket. The answer Einstein arrived at was a geometric picture. Gravity is not a force, but a curvature of spacetime. General principle of relativity. The trajectory of light as described by an observer inside an accelerating rocket is given by x equals ct, y equals -1/2 at squared, where a is acceleration and c is the speed of light. Substituting t equals x over c gives the curve y equals -ax squared over 2c squared. On the other hand, as seen from an external inertial frame, light follows the horizontal straight line x equals ct, y equals 0. The exact same physical phenomenon yields completely different equations depending on the coordinate system. Einstein therefore introduced two requirements. The first is the principle of general covariance. Physical laws must be written in a form that does not change regardless of the coordinate system used. This is where tensor formalism comes in, a branch of mathematics that deals with physical quantities independent of the choice of coordinates. It is a mathematical requirement that all physical laws must be expressed in tensor form in every coordinate system. The second is the general principle of relativity, a physical extension of the first. It requires that the laws of physics remain unchanged regardless of the state of motion of the observer. Here the two pillars of general relativity are united. The equivalence principle replaces gravity with the geometry of curved spacetime, while the general principle of relativity expresses all physical laws in the universal language of tensors. In this way, Einstein took gravity out of the hands of classical physics and set it free into the realm of geometry. This is the essence of general relativity.